The trick to this second idea is, let's take the water and figure out how much energy would we have to remove from the water to get it all the way down to the temperature of the ice. In other words, we start out with water at 10 degrees centigrade. How much energy would we have to remove to turn it into ice at negative 15 degrees centigrade? This is kind of like the first problem we did with the water, with the temperature and phase changes of the water going up, but now we're coming back down. So, to take 800 grams of water at 10 degrees centigrade and turn it into ice at negative 15 degrees Celsius, the first thing we do is cool the water. That's a temperature change, so Q1, this is a new Q1, it's not the same as the old Q1. Q1 is MC delta T, the mass of the water, specific heat of the water, temperature change from 10 to 0, 3.35 times 10 to the fourth. Then we need to freeze the water, we'll call that Q2. Again, we're talking about the water that we started with, so we're still talking about the 0.8 kilograms times the latent heat of fusion. This is 2.68 times 10 to the fifth joules. And then finally, once it's ice at 0 degrees, we cool it down to negative 15 degrees. We have to remove an additional energy, Q3, temperature change, 0.8, 2000 times 15, 2.40 times 10 to the fourth joules. We remove all of this, which is a total then of 3.26 times 10 to the fifth joules. But what's the point? Well, what do we have? We have now cooled the water down to negative 15 degrees. We have 800 grams of ice at negative 15. But we already started with 500 grams of ice at negative 15. So what we have now is 1,300 grams of ice at negative 15 degrees centigrade. We don't have two things that we're trying to figure out what's it going to come to, where are they going to meet in the middle. We've got one type of material at one temperature, which we now just have to add back in the 3.26 times 10 to the fifth joules. Oh, I forgot to mention the student that told me about this. I would mention who that student was, except I don't have his permission to use his name in this public forum. But if I ever hear from him and he says that I can quote his name, then I'll put it up. I'll put up a little Word box. So what's the problem now? We've got 1,300 grams of ice at negative 15 degrees centigrade, and we need to add back in 3.26 times 10 to the fifth joules. So let's do that. Again, we'll have to do this step by step to figure out how to do it, and I'll erase this and put that up. So what are we doing? We've got 1,300 grams of ice at negative 15 degrees centigrade Celsius, and we're going to add this Q4, 3.26 times 10 to the fifth joules, back into that ice, and we have to figure out what are we going to end up with. Well, the first thing that's going to happen is the ice will warm up, or will start to warm up to 0 degrees. Let's see how much energy that requires. So to heat the ice to 0 degrees, we'll call that Q5. This is a temperature change. So 1.300 kilograms, the whole mass of all the ice, times specific heat of ice, times 15 degrees is 3.9 times 10 to the 4 joules, which we notice is less than the 3.26 times 10 to the fifth. So yes, we have enough energy to heat the ice all the way up to 0. So we heat the ice to 0. How much energy do we still have left to add in? Well, we have to take this Q4 and subtract Q5, Q4 minus Q5. We'll call this Q6. So this is 3.26 times 10 to the fifth minus 3.90 times 10 to the fourth, leaving us with 2.87 times 10 to the fifth. Now, where are we? We've got ice at 0 degrees centigrade, Celsius. We still need to add 2.87 times 10 to the fifth joules. So what's going to happen? The ice will start to melt. Do we have enough energy to melt all of the ice? So how much energy would be required to melt all of the ice? Well, to melt all of the ice, we'll call that Q7. This is m times the latent heat of fusion, the whole mass, 1.300 times 3.35 times 10 to the fifth. That is 4.36 times 10 to the fifth joules. Well, to melt all of the ice would require 4.36 times 10 to the fifth, but all we have left to add is 2.87 times 10 to the fifth. We do not have enough energy to melt all of the ice. So how much ice does melt? Well, we use the same trick we did before. How much melts? We figure out m using the energy that is actually melting the ice, which is Q6, the 2.87 times 10 to the fifth. We divide by LF, and we get 0.857 kilograms. And we're done. So what do we end up with? Well, we have melted 0.857 kilograms of the ice, or 857 grams. So we end up with 857 grams of water. How much ice is left? Well, we had 1,300 grams. We melted 857 grams. We end up with 443 grams of ice. We were in the phase change of ice melting into water, which occurs at 0 degrees. Where it stops, it doesn't complete itself, and so we still must be at 0 degrees centigrade. At Celsius, and there we go. I had a student, I typically said centigrade, and a student of mine kind of actually asked me to call it Celsius, and so I'm trying to make the switch, but it's an old habit. So we are at 0 degrees Celsius, and there we go. Well, what did we have before? Using the other method, we had 855 and 445. It's very, very close. It's basically the same result except for rounding errors. As we put the numbers in, we rounded the numbers and we ended up with a slightly different result. But very, very close. You might think, okay, well, maybe there's another method that we could use where we go the other way. What if we took the ice up to the temperature of the water? We figured out how much energy would we have to add to the 500 grams of ice at negative 15 degrees to get it up to 10 degrees. We figure out how much energy we have to add to do that, and then we would take that back out, but starting at 1,300 grams of water at 10 degrees, rather than taking this down to here and starting at 1,300 grams of ice at negative 15. And we absolutely could do that. I won't go through that, but I think you can see the approach that you could use. Now, why is one of these methods better than another? If somehow you might guess what you're going to end up with, in particular, if you're going to end up with a mixture that's all water or all ice, if you use the method where you bring everything up to what that phase is that you're going to end up with completely, it's a much, much easier, very direct method of solving the problem. If, for example, if we had a very small amount of ice and we could guess that we were going to end up with all of it as water, well, if you bring the ice up to the water, you only have one more change after that to figure out what's the final temperature of the water. Likewise, if you happen to guess that you're going to end up with everything as ice, and you bring the water down to the ice, you'll have only one more step from there to figure out what's the final temperature of the ice. So, using this second method, I'll kind of refer to them as the first method, and this is the second method, and we have two possible second methods, say method 2A, method 2B. If you choose the correct second method, it can actually make the problem much, much easier to solve. And I'll leave those to some homework problems to give you some practice. The one difficulty that comes in, as I mentioned before, is if you end up with, say, all of the ice melted and you have some water that you started with and then all of the ice is melted as water, how do you figure out what that final equilibrium point is? Where all you know is how much energy the warmer water has still left to give to the cooler water. Well, what you can do is just figure out, okay, imagine you take that, switch immediately from method 1 to method 2. Remove that energy from the water, and that'll bring that water down to 0 degrees. Now you've got only water at 0 degrees, but you know how much energy you have to add back into it. It's whatever energy was left in the water to begin with. You put that back in, but now you put it into the entire mass of water, and you can very quickly figure out what the final temperature of the water is. So, switching from the first method to the second method, even if you started out in the first method, can really make the problem end up easier. Very, very good. One more lecture. I have some terrible, horrible, no good, very bad news. We only have one more physics lecture to go for this course. The last lecture we will spend going over some very, very general ideas of thermal physics. Just like we have 3 of Newton's laws that kind of are very, very basic laws that describe the area of mechanics, there are 4 very, very fundamental laws that describe thermal physics. They are called the laws of thermodynamics. In one lecture, we're going to try and get through the 4 laws of thermodynamics. It's going to be a brief overview, but I would like you to at least be able to see them a tiny bit. So, next time, we'll take a look at the laws of thermodynamics. I'll see you then.